In this video, we're going to talk about some deficiencies of the correlation coefficient. To quickly recap, correlation is defined as a covariance between two random variables scaled by the product of their standard deviations. Recall that we can estimate this correlation through the following formula here, where we take each of the samples, we subtract the mean, and we multiply them together to understand how they vary together, and then we scale them by their sample standard deviations. So in this lesson, let's take a look at a few examples of where the coefficient correlation may not behave in the way that we'd prefer. In this first image, we have Anscombe's Quartet, which is a toy dataset that was developed by Francis Anscombe to highlight the need for data analysis and visualization rather than just relying on a metric like correlation. In the first quartet here, we see some data that is correlated with a strength of 0.82. Visually, there looks to be a linear relationship between x and y, and this is demonstrated by the red line that fits the data. Now let's move on to the second quartet. We can visually see that there is some form of quadratic relationship between the variables. But if I were to blindly compute the correlation on this data set, I would compute a correlation of 0.82 again. In this third data set, we see an almost exact relationship, almost what I would say a functional relationship between x and y. However, we have one outlier here, and what that does is it causes our sample correlation coefficient to again be reported as 0.82. And in this fourth example, we see multiple values of y for a single value of x. But the outlier here forces that correlation to again be computed as 0.82. So the correlation is computed according to the formula that we displayed above. There's no error in computing the formula. It's just that the underlying data has more dynamics than the correlation coefficient is capturing, because there's no way to distinguish data in quartet 1 from data in quartet 2 using this single number here. And that's the point that we're trying to get across. So to push on these examples, let's take a look at two different functional relationships. In this scatter plot, we have a relationship between x and y, where x is a uniform random variable that goes between -3 and 3, and y is just equal to x squared. So given this equation, we know that if we know the value of x, we should be able to exactly compute the value of y. So they are perfectly dependent. They are functionally dependent. But when I compute the correlation is measured to be 0 here. And I'm showing the regression line here. That's something that we'll get to later. Let's take a look at another relationship, another functional relationship here where we have a log. So if we know x, then we can compute y by taking the log of x. So again, this is a perfect functional relationship, but here the correlation is measured as 0.87. So given these examples, really the question is can we use correlation as a measure of dependence when we're doing exploratory data analysis? And some of these deficiencies that I've highlighted here boil down to the fact that the correlation coefficient is a measure of linear dependence. Why do we say that correlation is a measure of linear dependence? Well, let's look at the relationship between regression and correlation. And these are formulas that are derived, and you can look them up elsewhere, but the relationship is, suppose I have a simple linear regression where y is related to x through a linear function with a bias of alpha and a slope of beta. Then given that, beta is actually equal to the correlation multiplied by the standard deviation of y divided by the standard deviation of x. So that means that correlation is a scaled version of the slope of linear regression. So the point of this is to show that linear regression and correlation are directly related to each other. And linear regression fits a straight line to your data, a linear line. And that's why you can think of correlation as a way to measure the linear dependence between two random variables. And Some of the deficiencies that we've shown earlier are a result of the fact that correlation can only capture linear dependence and not nonlinear dependence. If we wanted to measure nonlinear dependence, how would we do that? And that is actually the focus of our next video.